go through some examples on related rates. Last time in class we had spoke about implicit differentiation, and that was to get us to where we were looking at this new or different set of problems called related rates, and how to turn them into differential equations, and ultimately how to make models out of them. So what I want to do is I want to go through these exercises online. I got three different examples, three different exercises that I would have normally have you work through in class, but I'm gonna do them online so that you can see them and go back to them whenever you want. And the slides will be presented to you on Blackboard or be available on Blackboard for you to download them. So let's go ahead and get started. And let's go through a little bit of review from our last class on implicit differentiation. Again, implicit differentiation, unlike explicit differentiation, you can't solve the differential equation or do the differential explicitly in terms of one of the dependent variables. So what we're going to do, so what you have to do is you have to do it implicitly, meaning you've got to differentiate each term independently. So let's start off with an equation. X squared plus y squared equals 4. So we got basically that's a formula for a circle. And we're going to treat x as the independent variable, y as the dependent variable. And that's important because we go through this implicit differentiation, you'll see that, the one being x being the dependent or independent variable actually makes a difference in how we treat it when we go through our differentiation. So what we're going to do is we're going to differentiate each term independently, the x squared, y squared, and even 4. So you differentiate each one. The derivative of x squared is 2x. You got dx plus the derivative of y squared, which is 2y, dy dx, and the derivative of 4 is 0. That's important. So each term we differentiate, we have to show the derivative, as part of that, part of the function. So then we start into isolating the term we're trying to differentiate for, the independent variable, or dy dx. So we subtract 2x from both sides. And keep in mind this dx over dx is just a 1. So we can just ignore that. So we subtract 2x from both sides, and we divide both sides by 2y, and the 2's cancel. And we're left with our differential equation of dy over dx is equal to a negative x over y. When you're doing your implicit differentiation, the derivative of y needs that notation of dy dx, and the derivative of x, which is dx over dx, is just an implied 1. So from this point forward, whenever we do something with the independent variable, or the independent variable is in the function, we just treat it as an implied 1. You don't have to actually show dx over dx. Now, as far as doing a related rates problem, there's a certain process you can follow to help you walk them through. It's a situation that gives a lot of students some problems with related rates, and mostly it's because they don't have a real systematic way of approaching them. So here's some steps I want you to keep in mind, and I'll interpret each one of these. So determine the fundamental problem that's being addressed. Implicit differentiation or related rates problems are going to be given to you in the form of word problems. And particularly in this class, it'll be more of an engineering problem, or just some sort of problem where you're going to have to take a problem and turn it into a mathematical function. In order to do that, you're going to have to understand the fundamental problem that's being addressed. Next, you want to establish the change of rates that are being determined, as well as the constants. Okay, so now you're looking at what actually is changing and what actually is not changing, what actually is being set still. So are you looking at things like mass, which is a constant? Or is there some, are you given a constant velocity? Are you given a constant flow rate? Are there some variables, some features that are just simply aren't going to change? Establish the differential equation based on physical principles and geometric properties underlying the problem. So this is real key of related rates. establishing the difference between based on the physical principles and geometric properties. That's another way of saying what's the formula that relates all your variables together. Most differential or most related rates problems can be boiled down to a mathematical equation. We're going to see some that's based on geometry, some that are going to be based on things like heat transfer, some that are going to be based on something where you're going to have to actually deduce what it's based on. But typically there's an equation or a formula or something mathematical that already exists that you're going to have to base your related rates problem. That'll relate both your independent variables and your dependent variables, as well as your constants. Next is identify the differential equation and solve. Now, this statement is basically saying, now that you know what your dependent variables are, you know what your independent variables are, you've got an equation or a formula that relates them. Now you're going to start your implicit differentiation, because you're going to have to turn things into derivatives. Next, determine the arbitrary constant. So you solve your differential equation by integrating both sides, and you end up with a general solution. And then once you have an initial condition, or you can make a general assumption about an initial condition, you from that point turn it into a mathematical model, which is typically, unless you have to find some constant of proportionality, is typically just your particular solution. So let's look at some examples. So in our first example, we've got three we're going to look at. The first one is air is pumped into a spherical bladder at a rate of 120,000 cubic centimeters per second. Create a differential equation and a mathematical model for the radius of the bladder at time t. So what is this asking? So, okay, you've got air being pumped into a spherical bladder. And here they show these spherical bladders that I found online at a flow rate of 120,000 cubic centimeters per second. So the volume is changing at a rate of 120,000 cubic centimeters every second. We have here's these bladders that are being expanded at that rate. And what we want to know is a differential equation and a model for the radius of the bladder at time t. So our radius is changing. We've got a rate of change that lets us know about the volume, how much air is going into that spherical bladder. And we've got an independent variable at time t. So we've got this picture here of that spherical bladder, and then you see one actually inside a sewage pipe or some sort of drainage pipe. The real purpose for something like this is to stop flow of gases or liquids in the pipe so that repairs can be made. That's one of the typical. Another reason that someone might use this or a company might use this is as a safety mechanism. You might have something, gases in one particular chamber or some part of a building that you don't want escaping and get into another area. So a safety valve or a safety method might be to use a spherical bladder that can expand incredibly fast to block the passage. So these are just some of the reasons why this problem may exist. But going back to the problem itself, trying to make this more mathematical, this flow rate is a volumetric flow rate. So we got a rate of change of volume with respect to time. We're looking for a change in radius with respect to time, and time being the independent variable. We also know another thing, that this is a spherical bladder. So we know that got a rate of change of volume, rate of change of radius, and they're being related to one another through a sphere. So the relationship for the two rates can be addressed through the equation for a volume of a sphere, which is the volume is equal to 4/3 pi r cubed. So now that we know what our dependent variables are, which is time, or excuse me, which is volume and radius. We also know what our independent variable is, which is time. And we've got a way of relating to them, which is this formula, the volume of a sphere. Let's go ahead and do our implicit differentiation. So our rate of change of volume with respect to time, the derivative of that is just dv dt, which is also just the flow rate. Q is just the nomenclature for flow, or flow rate, is equal to the differential of 4/3 pi r cubed, which is 4 pi r squared dr dt. You know, these numbers are constants for 1/3 pi, but when you differentiate this r cubed, you end up with 3r squared, and the 3's cancel. So you end up with r squared, and then you got the dr dt on the other side. So we have created a differential equation. So our flow rate is equal to this differential, 4 pi r squared dr dt. So we got a rate of change of the radius with respect to time. Now, going back to our problem, what we're looking for here is the radius of the bladder at time t. So we're really trying to solve this for the rate of change of the radius. So we can consolidate this a little bit, which means isolating dr dt. In other words, we're going to divide by what is essentially 4 pi r squared, our variables. And we've set it up in the standard form of a separable differential equation. So since it's a separable differential equation, we're going to take a little bit of a step backwards here. We're going to multiply both sides by r squared, and then multiply both sides by dt. You end up with r squared dr is equal to the quantity of 4 pi, or q over 4 pi times dt. All right. Now, we integrate both sides of the equation since it's separable. And keep in mind that the flow rate, dv dt, or q in this case, is still a constant. This thing is, we're going to take this as a constant anyway in this equation. So you got a constant over 4 pi, which both are also constants. So this whole term here is a constant. So this constant goes on the outside of the integrand with respect to time. And as far as integrating on the left side of the equation, r squared dr, you end up with 1/3 r cubed is equal to the quantity of q over 4 pi times t plus c. So we got a general, or we're on our way to our general solution. What we're going to do is we're going to term this, or put this in explicitly in terms of the radius at any time t. We're going to multiply both sides by 3 and take the cube root of both sides. So you know, with 3/4 q over pi times t plus 3c raised to the 1/3. Now, as far as this 3c, I could have just called it c sub 2, c sub 1, and c sub 2, but I'm gonna leave it as 3c, just just so I don't end up taking something out of the equation without I'd rather give you an explanation than to make make that jump. Okay, so now we've got this in terms of just r. So we're going to take an initial value, and this initial value is based on an assumption that at time 0, at the time when this thing starts to blow up, that we're going to just say that the radius is 0. I make that assumption, even though technically the radius is not going to likely be 0. It means the thing doesn't exist, but it's close enough to 0 that we're going to treat it as a 0. And when you put 0 in here for at time 0 and a radius of 0, then what this eventually comes down to is that the constant of integration is equal to 0 once you go through the math. So this is what we end up with as our model. The radius at any given time t is equal to 3q over 4 pi times t raised to the 1/3. So that's the model that we could come up with, as well as the differential equation for that'll basically give us the related rate problem. So it shows the relationship between the volume of the balloon or the bladder as it relates to the radius of the bladder. And now we can create a model that is, or we have created a model that lets us know what the radius is at any given time. This is just a little bit of simplification, just taking everything out. I'm just going to 28.6 K times T raised to the 1/3. Let's see, our next example is a double acting hydraulic cylinder. It's a 10-inch diameter piston, or you can just call it a bore, but 10-inch diameter piston and a 2-inch diameter rod. So a rod on the other side, and a 4-inch stroke. So that means this thing travels 4 inches all the way till it retracts, and 48 for it as it extends. Excuse me, 4 inches as it extends. So 4-inch stroke in both directions. It's powered by a pump with a flow rate of 200 again cubic inches per minute. So we got a volumetric flow rate. Develop models that show the length of the stroke at time t for extension and retraction. All right. So here we have, let's look at this problem. So like you said, we've got a piston. We know the dimensions of the piston. We know the dimensions of the rod. We know how much flow is coming in from the pump. And we know the stroke is 4 inches. So the cylinder is literally a cylinder. So we got a cylinder. We know the cylinder at its maximum length, and we know it at its smallest length. We just say it's 0 when the stroke is 0, and when the stroke can be as high as 4 inches. So we know that the height of the stroke, or the height of the cylinder, or the stroke, is one of the things that's changing. We also know that we're putting this in terms of time, so in terms of minutes. So we can say that the stroke, as it relates to the volume of that cylinder, is what we're looking at. Those are the dependent variables, the volume and that stroke, with the independent variable being the time. And we know that the shape of it is a cylinder. On the other side, that's going into extension. Through retraction, however, you still have the same bore size, the same piston size. You still have the same stroke, but you have to take something else into account. You've got a 2-inch rod in the middle. Okay, so that's going to affect how much volume of fluid, hydraulic fluid, is actually going into this cylinder. So there's going to be more hydraulic fluid going in the extension side than there is going through the retraction side. So when we do this problem, we're going to have to consider how much fluid is not there, what that difference is. So ultimately what this is telling us, it's not only what the dependent variables are, volume and stroke, what the independent variables are, time, what the relationship is, the volume of a cylinder, but one other thing, that there's a model for extending the cylinder and a model for retracting the cylinder. So there's a few things we got to take into account. So we can relate to this through the volume of a cylinder. So let's keep that in mind, and that'll be for the extension side. So when we're extending, we're going to look at it this way, through the volume of a cylinder. So we got a volume is equal to pi times r squared, which is the bore, times h. In this case, h represents the stroke. Now, another thing I want to look at is understanding what the constants are. Now, with this equation, the constants are simpler and a little more straightforward. You've got a pi, which is not going to change, but something else is going to change. The radius. The radius on whether it's extending or retracting will be the same. So r is a constant. So we've got a constant for extension and a constant for retraction. So that's a constant. So the only variables here will be volume and stroke. So we can start looking at the differential equation, take the derivative of both sides. Well, actually simplify the equation a little bit. So just take pi times this constant of 5, just 10-inch diameter, 5-inch radius squared, which comes out to 78.54. So now we've got a constant as a numerical value for the constant. We can differentiate it. dV dt is equal to the 78.54 times dH dt. Isolate it and solve it for the derivative we're looking for, which is the rate of change of the stroke with respect to time. And it comes out as dH dt is equal to dV dt divided by 78.54 divided by our constant. And again, we know the rate of change of volume with respect to time. The flow rate is 200 cubic inches per minute. So 200 cubic inches per minute over 78.54. And if you do the math on the units here, you got cubic inches per minute over inches squared. So that does come out as inches per minute. We integrate both sides. And since this is a constant, it just comes outside the integrand, and you end up with the rate of change for the height of the, rate of change of the stroke with respect to time, or the stroke at any given time t is equal to 2.55 times t plus the constant of integration. So again, let's make an assumption that when this thing is all the way collapsed in, and you're about to extend it, we'll just say that the stroke is at 0.0. So at time 0, it's at height 0. So we plug that into our equation. We end up with the actual model of the height at any given time t, the stroke at any given time t, is equal to 2.55 times t. So that's our first model. That's the model for extending the cylinder. We have a different issue when it comes to retracting the cylinder, because we're going to have to figure out how much fluid is not being put in here based on the rod that's going to be in the way. So we're taking a smaller volume. And the way we do that is we just take the difference between the two radiuses. That's, the difference between the two radius squared. So again, we got our constant of pi, and this is going to remain constant no matter where it's at and at any given point in time. So we only have two dependent variables, volume and height. So we're going to look at this in terms of retracting, put in our actual values since they will be constants. We come out with the volume is equal to 24 pi times h. Differentiate both sides, and we get the rate of change of the volume with respect to time is equal to 75.40 times the rate of change of the stroke with respect to time. Divide both sides by the constant. We integrate both sides. We end up with a general solution. The stroke is anytime t is equal to 2.65 times t plus c. Let's make that same assumption that at time 0 that the cylinder is fully extended. So it leaves us with just a mathematical model of our extension. So the stroke at any time t is equal to 2.65 times t. So slightly different, but definitely a different model between the two. Our next one is develop mathematical models to find the velocity and displacement of a particle at any time t. At 0 seconds, the particle traveled 0 meters, and the particle has a constant acceleration of 5 meters per second squared. So this one's a little bit different. We're trying to come up with mathematical models for 1, the velocity, and the 2, the displacement. They give us an initial value at 0 seconds, go at 0 meters. So we know, it's got some sort of initial value we're going to work with here, so we don't have to make any assumption on that one. They give us a constant. The acceleration is the constant. Again, these are all done with respect to time. So that's our independent variable. So we got our dependent variables as velocity and displacement. But something else that makes this a little different than our other two examples. Velocity and displacement have a distinct relationship between acceleration. We can look at that a little bit more. Basically, our velocity is the rate of change. Well, let's start from here. The acceleration is just the rate of change of your velocity with respect to time. So acceleration is the derivative of velocity. And displacement, or velocity is, hold on, I get that backwards. And velocity is the derivative of displacement. Okay, so rate of change of displacement with respect to time gives you velocity. Rate of change of velocity with respect to time gives you acceleration. So the antiderivative of both of these, of acceleration, gets you your velocity. The antiderivative of velocity gets you displacement. So let's look at the model for velocity first. The relationship of velocity to time. Our acceleration is the derivative velocity with respect to time. You can just solve that for dv because we're looking for what our velocity is. So we'll treat it as a separable equation. Integrating both sides, treating this acceleration as a constant, we can plug that in because we know it's 5 meters per second. As we integrate both sides, we end up with the velocity at any given time is equal to 5t plus c. We got an initial condition. We know that at time 0, the particle hasn't traveled. So basically, we're taking that as our initial condition at time 0 that the velocity isn't being reviewed. So we end up with a constant of integration of c. So our velocity at any given time t is equal to 5t. So this is our model for our velocity. Now looking at our model for our displacement, again, your velocity is the derivative of displacement, or just displacement with respect to time. Do our cross multiplication, end up with the integral of ds is equal to the integral of velocity with respect to time. Integrating both sides. First, we can look at we integrate one side with the displacement with respect to our displacement at any time t is equal to the integral of this function that we came up with in our last model. And we integrate it, substitute in for velocity, and we integrate it, and we end up with 5, which is a constant, and time squared over 2 plus c. So we got a general solution. In our initial condition at time 0 seconds, the particle traveled 0 meters. So our displacement is literally 0. So we put in our initial value. I got a c of 0. Our displacement at time t is equal to 5/2 t squared. So we got a second model for our displacement at any given time. If we map this out, looking at the velocity at any given time, it does fit that model. At time 0, it's 0. Our velocity 0 at time 2, velocity is 10. At time 4 seconds, the velocity is 20. So you can see this thing is accelerating, and it is accelerating constantly. So it is a linear condition we're looking at here. All right, so that is the 3 examples I wanted to work with. Hopefully you can get something out of it. Look it over as you need to. Any questions, you can get me in my office hours, or send me a text, or ask me questions online. But this is Professor Cummings again, just going through some examples of related rates problems. All right, thanks a lot.